Okay, today is day 9, and we're going to continue today with inverses and add in logarithms. Probably the pace today will be fairly quick, but I'm hoping this is going to be a review for you. So we'll deal with kind of what we're going to use inverses for, how to find them, how to graph them, the original function and the inverse. Look at inverses of exponentials, which are logarithmic functions. What's a logarithm, by the way? It's kind of a fancy word for what? It's a power. It's an exponent. Okay? So when you see the word logarithm, it's nothing more than just a fancy word for an exponent. So we'll look at logarithmic functions, and specifically the inverse of the natural exponential function, which is what would that sound like? The inverse of the natural exponential function. The natural logarithmic function, okay, the natural log function. So we'll look at all that today, so I think we'll be flying, but I hope most of it is familiar to you. We ended yesterday with the fact that if we compose a function and its inverse, we're back to the original element that we began with. So if we have the f of the f inverse of x, might actually want to write it so you can see it. Would think that would be helpful? That help? I realize this one doesn't have quite the same viewing area, so let me work with that. So we're going to take the f of the f inverse. And I think I showed this with a diagram and a mapping and a pairing, that we took a set and we flipped it around, and 4 was paired with 7 in one set and 7 was paired with 4 in the other set. So we did that and we ended up with the same thing that we started with. So if you compose a function with its inverse, you're back to the original element. And the other way around, the f inverse of the f, if you start with x, you end with x. So if that's true in both cases, f and this thing we're calling f inverse, it's a good thing they're inverses since we called it that, are in fact inverses of each other. Now, rather than prove one of these now, let's wait till today we start with the function and we find its inverse, and then we'll come back to this validation or verification to actually prove that the function that we found is indeed the inverse of the original function. So hang on to that for an example. We could I guess maybe look at a quick one, although we're not finding the inverse. I think we talked yesterday about the squaring a function and taking the square root. Those two, squaring and square root, seem like they're inverses of each other. We got a little bit of a problem there because of possibly one of those not being 1-to-1. So let's stay away from squaring and taking the square root and look at cubing and taking the cube root. So if we take, let's just go one way with this. We're starting to lose that one a little bit. This is probably overly simplistic, but that's why I'd rather look at it again with another example. The f inverse of x, well, the f inverse is cube root of x. So we take the f inverse first. You do what's inside the parentheses first, and then what do we do with whatever is inside the parentheses to take the f of it? Cube it, right? So we're going to take in cube whatever element is inside the parentheses. Well, we're cubing the cube root, so it's not a mystery that if you cube the cube root, you're right back where you started. So we started with x and we ended with x. But we'll when we find one in a couple minutes, we'll validate the fact that it is in fact the inverse. I'm afraid I'm going to forget to do this, so I had somebody after class yesterday, and then Tiffany today asked me to take a look at a problem from the previous homework set, page 63, number 15. So I'm afraid I'm going to forget, so let's do that. So page 63, this is from section 1.5. Sorry to kind of interrupt here. Yes?
If we had any more questions, do you not want to ask now?
Let's get to this one, and we'll kind of see how the time goes. And do you have a lot of questions?
Just one.
One other one?
Just one part to one question.
Okay. Well, we'll see. So I'm looking at problem 15. It says find the exponential function. So we want to find some f of x in the form of c, which we don't know at this moment, times a, which we also don't know, raised to the x, whose graph is given. So it looks like the graph is exponential, so it seems to work. What do they give us? They give us 1, 6, and 3, 24. Anybody meet with success on this problem, and how did you go about it? Had a couple of questions, but maybe we've got other people that have a question that just haven't vocalized that yet.
Take your
Harold.
y values and then plug it in for f of x. Then set x, place x is 1.
Okay,
Then you have 6 equals c times a raised to the 1. Then you
everybody
solve
like
for
that?
C.
Basically, you just plug in the points. Don't the points have to work in the equation? So Harold is saying that just instead of calling that f of x, we can certainly get away with calling it y. Those are the paired y values. So 1, 6 has to work in that equation. So y is 6. C we don't know. A we don't know. But the corresponding x value is 1. Is that all right with everybody? Does that help the cause? Don't we get a nice little interrelationship there between A and C, right? Basically, 6 is C times A. That should probably help. Should we do the same thing with the other one?
Well, I solve for c, then you know what c is. Then you take the other equation, and I set it, or I did the same thing except for I placed c with 6 over a.
Okay. So why don't we, so eventually you did this, so right? You plugged in 3 and 24?
Yeah.
Okay. So let's do that, and then we can use your method of combining the two equations, and I think that'll work for us. So let's plug into this equation again. Y is 24. C we don't know. A we don't know, but when y is 24, the corresponding x is 3. So everybody go along with that? Those two equations have to be true. Now there are some different techniques of how to solve two equations in two variables, but we ought to be able to somehow get a solution. And Harold's suggestion is to substitute for C or A, which one?
C.
For C? Okay, what is C equal to from the
6
first
over-
equation?
6 over a.
Take this equation and solve for C. C is 6 over A. And then we'll take that and we'll plug that in for C in that position. So 24 is, instead of C times A cubed, we're going to plug in 6 over A for C. Everybody all right with that? So that is, in essence, a combination of the two equations with a substitution to eliminate C. So 24 is 6a squared. Divide both sides by 6. 4 is a squared. Now, did they say anything about any provisions about a? I don't see that. So could a be positive or negative?
Can't be negative.
Can't be negative.
Can't be negative.
I mean, don't you agree, though, that A, if we solve this equation, could be plus or minus 2? So that's the algebra, but do we need to, with the picture, throw out negative? I think we probably need to throw out the negative base based on the picture that was handed to us. So let's lock into the single A value of 2. And if A is 2, then we can come back here to this interrelationship between C and A. And if C is 6 over A, C is what? 6 over 2, which is 3. Are we in business now? The two things we didn't know, we now know. So if we come back and try to put our equation in this form, f of x equals c times a to the x, we found out that a is 2. We found out that c is 3. Does that seem to work? Can you try those 2 points in a matter of seconds? I urge you to do things like that. The 0.16 better work. Does that work? If x is 1, y is 6, that works. It just takes a couple seconds. And the 0.324 should also work. Does that work? So they both work. It is exponential. So I think we've solved that. So basically, take the points that you're given, sub them in, try somehow to consolidate those 2 equations, and instead of having 2 equations with 2 variables, consolidate them into a single equation with a single variable, and go from there. Any further question with that one? What's your question? Let me see how quick I think we can get to it.
23, part D.
I may have to table it to when I know I have more time, because I know we're... Okay, page 64, number 23. Under ideal conditions, a certain bacteria population is known to double every 3 hours. Suppose there are initially 100 bacteria. What is the size of the population after 15 hours? What part of that?
Part D.
Part D.
Mm-hmm.
Graph the population function and estimate the time for the population to reach 50,000. I'll tell you what we'll do. Let's get the equation.
Mm-hmm.
And then when we get logarithms, which we're going to review today, and we need an example, I'll come back and I'll do this as an example.
Sounds
but
good.
let's get the equation first. So this is page 64, number 23. So the setting or the things they hand us, under ideal conditions, a certain bacteria population is known to double every 3 hours. So since it's a doubling type function, let's use base 2, right? And if it doubles every 3 hours, I think we did one example like this, right? That we want this 2 to a power to be 2 to the first when we plug in 3, because we want it to double. Does that make sense? We want it to double when we plug in 3. So that'll happen when we put a t for time in the numerator and divide it by 3. 3 divided by 3 is 1. That's what we want to happen, 2 to the 1. And then this should be our initial amount, which is 100, that occupies that position. And that's our function of t, or capital P of t, whatever you want to call it. There are a couple of points that you can kind of plug in here and make sure that they work. We know that at time 0, the amount of bacteria, so the F of 0 should be what, 100? Is that correct? Does that work in this equation? Do we initially, at time 0, have 100 bacteria? That works. And then we know at time 3, what should we have? 3 hours later, if we started with 100, we better have 200. So in that sense, it's a lot like the problem we just looked at. Is the F of 3 200? Mm-hmm. It is, right? And then it should double again after another 3 hours. Mm-hmm. So So there's the function. Let's hang on to that function, 100 times 2 to the t over 3. And then the problem that we want to answer in a few minutes, we won't do it from the graph, we'll actually solve it. Estimate the time for the population to reach 50,000. So time equals what? Whenever the variable is in the exponent position, we're going to have to use some kind of logarithms, right, to solve for that variable. So let's get to that point and we'll come back and solve this problem. Okay, questions on that much of that problem that we actually did, and we'll get the solution later? Any other quick questions from 1.5? 24, part D, is that similar?
Yeah.
That's similar. Now, is it use the graph to estimate? We'll hopefully answer that. And to be real honest with you, I mean, using your graphing calculator is a nice estimation tool, but when we finish today, we'll have the ammunition to get an exact solution without trying to read a graph or a sketch. So let's table both of those to after we've reviewed logarithms, and then we'll get an exact method of solution. Anything else? Any other question I can totally delay and skirt around here today? We'll get to it. Throw something at me if we don't. Okay, well, let's pick back up then with the rest of 1.6. This piece, the first part here, I believe we reviewed yesterday. That's the composition of a function and its inverse. We got that again today. So if you compose them, doesn't matter the order in which you compose the two functions, you're always back to the original element that you started with. That means they're inverses. Okay, let's get to the place where we can take a function and find its inverse. Here's what your authors suggest. I don't know what you're used to, but I'm going to alter this just a little bit. How to find the inverse of a, notice, one-to-one function. So that's one of the examples I have is not one-to-one. So that's our first task, is to make it one-to-one and then find its inverse. So write the function and we'll replace y for the f of x. It may be actually handed to us in the form of y equals f of x. Solve this equation for x. I actually kind of do these things in reverse, but I accomplish the same things. The author suggests solve for x in terms of y and then interchange x and y. I like to interchange x and y first, and then instead of solving for x, I can solve for y. I don't know what you're used to, but they both work. But I will typically interchange x and y first and then solve for y. Any preference? Okay, then we'll do it my way. How's that? Okay, let's have an example of a function where we do this. Let's start real simple. So we want to find the inverse of a linear function. Now some of you, when you get good at this, you may be good at this already, you could look at a linear function or look at a simple quadratic or a simple cubic and tell me what the inverse is. Anybody do that? Anybody tell me right away just by looking at it what the inverse is?
X is equal to 2y minus 1.
Okay, but solve for y. In other words,
Y equals
f
1 half
inverse.
plus 1.
Say it again,
1
Harold.
half plus 1.
1
1 half
half,
x plus 1.
1 half x plus 1. That's pretty close.
X plus 1.
Okay, now let me get to why you said that, Harold, and then I think we got it. Why did you say 1 half?
Well, you just, I don't know, I solved for it, but you can look at it and just say, if you just take inverse of 1 half or 2, I mean, then it'll be 1 half.
Okay,
And
everybody go along with that? Instead of on this one, we're supposed to double. Doesn't it make sense on the inverse that we would sometime take 1 half, right? Doubling and 1 halving sound like inverse operations. And then the other part to that is this one has subtraction of 1, so Harold said what?
Addition.
Addition of 1. So we ought to have, see if we don't have when we're done, the opposite operations in the opposite order is what should happen. All right? So we're really starting with 2x minus 1. Now, this is not manipulating the same function. We're going to find a new function. The new function is the inverse function. So I'm going to switch x and y. Everybody all right with that? And now we're going to solve for y. Now that may be what you said. Now I heard 1/2 x plus 1. We've got to be, I guess, a little careful about how we say it. Isn't it 1/2 the quantity, x plus 1? Or x plus 1 multiplied by 1/2? Now, is that, and I'm going to call this f inverse. Now, does that look like to you that from the function we started with and the function we ended with, which is a completely different function, completely new set of points, that we have the opposite operations done in the opposite order? What's the first thing you do to x right here in this function? If you were plugging in a number for x, what's the first thing you do? Multiply by 2. What's the last thing you do to x, to the variable quantity here? Divide by 2. What's the second thing or last thing you do to the variable quantity here? Subtract 1. What's the first thing you do to the variable quantity here?
Add 1.
Add 1. So you can look at a linear function and basically do the opposite operations in the opposite order, and you've come up with the inverse. I said we'd do this, so let's do this with this example. Since we just took the function and found its inverse, let's see if we can compose them in this direction and also this direction and get x. So we know that f of x was our original, and f inverse is what we found. So the f of the f inverse let's take the f inverse first. We'll do what's in here first. So the f inverse is this. And then how do I take the f of something? Don't I double it and then subtract 1? Yeah. So whatever I'm taking the f of, I'm taking the f of this whole quantity. So I want to double that whole quantity and subtract 1. Now, I mean, everybody knows it's going to work because that's how we found it, is we kind of undid everything that was being done to x. So the 2's reduce, you've got x1, x plus 1 minus 1, which is x. So that direction it works. We started with x and we ended with x.
So what if you put the value of x as 2x minus 1? Like 2x minus 1 plus 1.
Okay, that's what we're going to do now. We're going to compose them in the opposite order. So we're going to take the f inverse last. We're going to take the f first. So we'll take the f first, which I think is what you're talking about. So the f of x is 2x minus 1. And then how do we take the f inverse of something? Add 1 to that. Take that whole mess and divide it by 2. So we put it in the variable position right here. So instead of x plus 1, it's 2x minus 1 plus 1, and then divide the whole mess by 2. Minus 1 plus 1 is 2x over 2. So that's enough right there to validate that these are in fact inverses. We knew that because we started with one and found the other, but this, if we didn't know that, this would verify that they're inverses. So whenever you're asked a question, are these two inverses? They hand you two functions, or I would hand you two functions. You could use this process, right? compose them in both directions, get x in both cases. That validates inverse. Or you could start with one of them and find the inverse and show that it's the other. So you have a choice. Okay, let's take this as a second example. Got a problem. Tell me what it is.
1 to 1.
Not 1 to 1. So the first task is to take our original function. It is a function, but it's not a 1 to 1 function. Looks like this. So clearly, it does not pass the horizontal line test in a lot of different instances, so it's not 1 to 1. What can we do when we have a function that's not 1 to 1 and we want to work with part of it so that we can find the inverse of that part that is, in fact, 1 to 1? Well, if I had an eraser here, I could just erase part of it, right? Well, let's just do that by saying the domain is x is what? Greater than or equal to 0, right? So if we do that, if we restrict the domain on the original, we have that set, which certainly is clearly related to the original set, but it isn't the entire set. But that is 1 to 1. So if we restrict the domain on the f, what ends up being restricted on f inverse?
The range.
The range, because the domain of f becomes the range of f inverse, right? Mm-hmm. So here's our function with this little addendum here. We're going to restrict the domain. Now we want to find its inverse. So here's our original. We want to find a new function. So we interchange x and y, and now we want to solve for y. So we've got x minus 2 equals y squared, and what else? Square root. Now, when we take the square root, don't we have to allow for both possibilities? Mm-hmm. Typically we do, so let's do that first. But do we actually want both of them? No. I don't think we do, because I don't think this would even be a function. Let's come back here. Here we said that the x's were greater than or equal to 0, so when we come down here, what's that say about the y's? The x's in the original become the y's in the inverse, right? So up here, the x's are greater than or equal to 0 tells me that down here, the y's better be greater than or equal to 0. So do I want plus or minus the square root? No, just plus, because of that fact. The domain was restricted up here, which tells us the range is restricted down here. So we just want the principal square root only, which you don't need to put anything there if you want the principal square root. So what do we have? We have our original set with the restricted domain, and then we have our inverse, which was the principal square root of x minus 2. Is that the opposite operations done in the opposite order? Does that work here? What's the first thing you do to the variable in f? Square it. What's the last thing you do to the variable quantity in f inverse?
Square root.
Square root. That sounds to me like opposite operation. And what's the last thing you do up here to the variable quantity?
Add 2.
Add 2. What's the first thing you do down here? Subtract 2. So it is the opposite operations done in the opposite order. Now, if you know the domain of f, which we do because we kind of decided that ourselves, we had to make it 1 to 1, then we automatically know the range Now, if I can find either the range up here or the domain down here, aren't they the same? Which one do you want to find?
The domain.
They're both about the same here, right? Is it fairly tame to find the range of the first function? Can you see that? Visualize that picture. We've already pictured it. What are the y values? 2 and higher, right? Now, let me just write this down here. Is that true down here? Does that make sense that that's the domain? It does, doesn't it? Because we're going to take the square root of something. That something better be 0 or larger, or we're in trouble. So if you know the domain of one, it's the range of the other, or vice versa. Whichever one is easier to find, then you can pair it with the domain or range, whichever one you need in the other set. Okay, graphing. What am I doing over here? I guess I'm trying to keep track of how we look over here. You know, one thing nice about this is when I teach and write on the board, you kind of are forced to, in a certain sense, watch me. And you don't have to do that in here. That's a nice little luxury on your part. You can listen to me, but you never have to look at me. And believe me, I check a mirror once a day. And it's not the most desirable thing, what I'm seeing in that mirror. So that's pretty nice. You get to watch the screen instead of watching me. When you graph a function and its inverse, tell me visually how they appear on the same coordinate plane. Nobody besides Harold. Harold's answering everything today and answering it right. People are going to be mobbing him on the streets when they watch this on cable TV saying, gosh, that Harold, man, I got to talk to him. He knows everything about math. I don't want him to come to him too much and wear him out. How about when you picture a function and its inverse on the same coordinate plane? Umar.
There will be a reflection in y equals to x.
Y equals
X. That
x.
line.
Does that sound familiar? Right? So if we take our original function that we just looked at, the restricted version, and if we graph them on the same coordinate plane, is that it? Is that these two? And if we took the mirror image of one or the other and basically took the symmetric image on the other side of the line y equals x, I think we have the inverse. And I think I've got something up here that kind of explains that. Is that right? Is that something you remember about graphing a function and the inverse? If you're graphing one, how can you come up with the graph of the other? If you've plotted some points on one, what do you do to those points to come up with the
Switch the X and Y.
switch them, right? Switch the x and y, just exactly what we did with the functions themselves. Okay, this is in your text. And the only reason that I wanted to show this, I mean, it's got a couple of nice pictures here, but there's some good old-fashioned high school geometry here, which I'm sure you've told me on several occasions that it was probably your favorite subject in high school. All of you in here told me that. No, you didn't. Most people don't like high school geometry. Actually, it was my favorite to teach. Talks about the graphs of the inverse of a function and reflecting a point or reflecting the whole graph about the line y equals x. Here's a point AB and here's its symmetric image on the other side of the line y equals x. Now, little high school geometry here. Everybody agree that this little triangle is congruent to that little triangle? Could you validate that by sides and angles and, right? I think we could do that. Now, are we also then able to get this little triangle congruent to this little triangle? There's some more high school geometry there, right? The right triangles, and if you had to, you could get, this would be the hypotenuse of the one that I've shaded green, and this is the hypotenuse of this one, right? The hypotenuse of one is congruent to the hypotenuse of the other. They are right triangles. And then this leg ends up being congruent to this leg. You can get, using a variety of techniques in geometry, you could prove those triangles that I've shaded green here are congruent. And if they're congruent, that means that this line segment, let me rephrase that, that the line y equals x is the perpendicular bisector of that line segment. So that line is and whenever you talk about it being the perpendicular bisector, then one point is the symmetric image of the other one reflected about the line y equals x. So here's a couple of sketches at the bottom of this. These are also in your book. If this is f, its symmetric image on the other side of the line y equals x is this. If this is f up here, then its symmetric image on the other side of the line y equals x is this. And if you have one, all you have to do is flip the points around and start plotting them, and you can get the other. That perked you up. Get a little high school geometry flowing. I can tell what that did. Okay, let's go on to a special type of inverse. In fact, this is one of the main reasons we're doing this, and this would be logarithmic functions. So if we want to start with a function that is exponential, interchange the roles of x and y, then we're kind of stuck unless we come up with some special kind of name. Let's say that we have an exponential function. And we want to find the inverse. So we've got y equals a to the x. Now we want to find the inverse. We find the inverse by switching x and y. So here's where at some point in time somebody had to develop their own little language. Somebody a whole lot smarter than me developed their own little language that says, okay, I want to solve for y, right? Isn't that the next thing to do? Okay, where is y? Y is in the exponent position. So y is the power to which a is raised to get x. Well, that's not going to make it. We got to have something a little more concise than that. That's what y is. That's a description of what it is. Okay, well, y is, I can translate that. That's y equals the power to which a is raised. Okay, what did I say earlier in class is a fancy name for power or exponent? Logarithm. To which a is raised. So there's some mathematical lingo there that says that we're describing what y is. It's a logarithm. It's an exponent. So y is an exponent to which a is raised to get x, right? So here was our original function. Here is its inverse. So if we want to deal with exponential functions and we want to talk about their inverses, then we're more or less forced to incorporate logarithms of one base or another. And we could compose them, right? The f of the f inverse, and we'd be right back to x. I'm not going to do that with these two, but I mean, you should be prepared to do that, to compose any function with its inverse. So let's take something of that form. Y equals 2 to the x. The inverse, this is basically the same thing we just did. Switch the roles of x and y. Y is the power to which 2 must be raised to get x. So y equals 2 to the x and y equals log to the base 2 of x ought to be inverses. 2 to the x. We know what that looks like. So can we take the graph of 2 to the x, flip a couple points around, and come up with the graph of y equals log to the base 2 of x? If we were plotting a few points on this one, what would be some good choices to make? Let's say we don't have the graph of y equals 2 to the x. We want to generate the graph of log to the base 2 of x. We could plug in 1. That might be log to the base 2 of 1. I'm just trying to get you to think in the logarithmic mode. What are we looking for? We're looking for log to the base 2 of 1. That's the power that you would raise 2 to get 1. What is that answer?
0.
0. Okay, let's suppose x is 2. This almost answers itself if you ask it the right way. What power do you raise 2 to get 2?
1.
To the first, right? You raise 2 to the first to get 2. So there's a couple of points. So if you pick and choose, you can get enough points to get started. Well, this is the point 0, 1, so we should expect the point 1, 0. This is the point 1, 2, so we should expect the point 2, 1. And we end up with that set, right? The mirror image of our original set flipped over the line y equals x. Okay, let's look at some, review some properties of logarithms. Again, these are in your book. So the first one is kind of an interrelationship between a logarithmic form of an equation and the exponential form of the same equation. These are both true simultaneously. Now we started over here. We said a to the y equals x. Therefore, what is y? Y is the power to which you would raise a to get x, right? These two are 100% the same thing in the first line on this page. So if one is true, we took a look at that yesterday, didn't we? That biconditional, the arrow that goes both ways. If the first is true, automatically the second is true. If the second is true, automatically the first is true. So an if and only if statement. So one automatically leads to the other. The second little block here are some logarithmic properties that, again, if you ask yourself the question the correct way, they should, in a sense, answer themselves. When you're looking for, well, what do you really ask yourself right here when you're trying to figure out what that side means? Log to the base a of a to the x. Aren't you looking for the power that you would raise a to get a to the x? Right? when you have this statement right here, aren't you looking for the power that you would raise 2 to get 8?
Right.
Right? So what are we looking for here? We're looking for the power. Now listen to my question. What power do I have to raise a to get a to the x?
X.
X, right? What's the name of your brother whose name is Bob?
Bob.
Right? Well, that's not Steve, right? The name of your brother whose name is Bob is, for goodness sakes, Bob, right? That's the same kind of question. It's just a mathematical question. So what power do you raise a to get a to the x? For goodness sakes, you raise a to the x to get a to the x. Okay, now this is a little different one. It's similar, but it answers itself. What power are you raising a in that statement?
Log base 8. Yeah.
Okay, you're raising a to the power that you would raise a to get x? Isn't that what this means? That's the power that you would raise a to get x? Now, listen to this now. What should you get when you raise a to the power that you would raise a to get x? You better get x, right? That's all this says. Now that is only true because they are inverses of each other. Do you see that this is really a composition of an exponential and a log? This is the composition of an exponential and a log. So what should you get when you compose an exponential and a log when one was derived from the other? You ought to get back to the variable you started with, right, which is x. So this is kind of a further validation that when you compose a function with its inverse, you get the element that you started with. Okay, here's some laws of logarithms. I'm going to ask you a question that maybe you've never been asked before, but I know you know these. But I'm going to ask you why these work. Why is the log of a product the sum of the logs? That's what this says, right? The log of a product is the sum of the logs. What are logarithms again? Exponents.
Exponents.
And how do you multiply two numbers with like bases? You add their exponents, right? That's it. That explains it. That's all we're doing. We've got a log plus another log, right? Why? Why are we adding logs, adding exponents? Because we are doing what to the numbers they represent? We're multiplying it. We're multiplying x and y. Therefore, we can add their exponents. Doesn't that also make sense here? What do you do with exponents trying to divide two things with like bases?
Subtract.
You subtract the exponents. That's all we're doing right here. This exponent minus this exponent. Now, does that same rationale hold true down here? What do you typically do when you're talking about the something raised to a power that is itself raised to a power? What can you do with that? If you have 2 to the third, which is squared, what can you do with those exponents? Can't you multiply them, right? So isn't that really what we're doing here? We're multiplying this exponent by this one. Same deal, exactly. So if to raise something that's already raised to a power to a higher power, you multiply the exponents. This is the logarithmic property that is the counterpart of that. So if you know how to deal with multiplication and division of two numbers with like bases and how to raise a number that's already raised to a higher power, these ought to make a whole lot of sense to you. Okay, and let's finish today quickly, or at least start for a couple of minutes with the natural log function. So we have a natural exponential function, which is this. Talked about that yesterday, that crazy number e. And then the inverse of that Well, let's find it. So the original is y equals e to the x. So the inverse ought to be x equals e to the y. What is y? Y is log to the base e of x. Now you don't see that notation very often. It's legal. But typically log to the base e we write as what? ln, right? So y equals e to the x and y equals natural log of x are inverse of one another. So if f of x is e to the x, then f inverse is natural log of x. Let me put these properties up here. They ought to look familiar to something that's already been up here. One of them we just wrote, log to the base e of x, we typically write natural log of x. It's not wrong to write the other, by the way, but I think you're probably used to writing natural log of x. These two statements are equivalent to one another. Basically, we just did that. We just used them ourselves. Here we go with the self-answering questions. If you want to think of these as the composition of a natural exponential and a natural logarithmic, they're also that. What power would you raise e to get e to the x? X, it answers itself, right? Mm-hmm. What is this exponent right here? That's the power you'd raise e to get x. What do you expect to get when you raise e to the power that you would raise e to get x? Well, for goodness sakes, you better get x, right? So those answer themselves. And then the last one, natural log of e is 1. Is that right? Natural log is a base e log. What power would you raise e to get e? When you raise e to the 1 to get e? So that comes in handy. The fact that the natural log of this crazy number is a real simple number, 1. I want to do some examples tomorrow, but we're finished today. You can get a start with these problems. If you don't feel comfortable finishing the whole thing, feel like we need some examples, then I'll actually have these due the following day. These are on page 73. You know what I didn't do today? I didn't finish that problem. Don't let me get away with that. Remind me, and I'll make that one of my examples tomorrow, and we'll begin class with that. How long would it take for the bacteria that double every 3 hours to be 50,000? We'll begin class with that tomorrow.
You said these aren't due tomorrow?
Not due tomorrow, but there's a good likelihood, though, that once we've gone through this completely, that this set of problems will be collected. So I would get, if not all of them done, a good part of them done prior to tomorrow. And that finishes day 9. I will see you tomorrow.